In this section, we look to talk more deeply than probably you ever have before about things like perpendicularity and things of that nature. So with this in mind, let me go and start a definition. So I'm going to let U and V be vectors in Rn. Define the inner product of U and V to be, the notation we'll use is this: U dot V, and this equals U transpose V. So in calculus, we call this the dot product. You'll see those words thrown around. Inner product is probably more what is used in math courses when you get more theoretical, because the idea of perpendicular or dot product, sometimes they need to be generalized for more complicated or more abstract spaces. So anyways, if let's let U say equals U1, U2 up to UN, and V equals V1, V2 up to Vn, then U dot V, that's U transpose times V. So what we'll do then is we'll put U on its side. That would be the transpose of U, multiplied by the vertical vector V1, V2 up to Vn. And we've been doing this, we've done this all through the course. This is just equal to U1 V1 plus U2 V2 plus all the way up to UN Vn. Most of the time, when I do these, I typically won't go through all the effort of doing this kind of stuff. I'll just start taking the dot product. Let's go ahead and do an example to illustrate this thing. So, for example, if I have U equal to 1, 2, 3, and V equals 4, 5, 6, then when I do U dot V, that's U transpose V. I'll put my U on the side, 1, 2, 3. My V will stay vertical, 4, 5, 6. And then you multiply this as you normally multiply matrices together. I'll have 1 times 4. Then I'll have plus 2 times 5 plus 3 times 6. That'll be 4, 14, and 18. Looks like 32. One way to see this, I think, is that U dot V is equal to the sum I equals 1 to n of Ui times Vi, and those of course are real numbers. Now, of course, when you're multiplying real numbers, I can swap, I guess you call it, the U and the V, because R is commutative. So what I did is I swapped those in the realm of the real numbers. And this, of course, is then going to equal v dot u. So the dot product, or the inner product, is commutative. And the other things that we might have, u plus v, if I take that and dot it with w, then I think it's easiest to see when you're proving things about it to go to the sum. We'll have ui plus vi times wi, and I can distribute the wi's in and get ui wi plus vi wi. That's according to the rules of multiplication in ordinary real numbers. A sum like this I can break up into a sum, I equals 1 to n, of ui wi plus the sum I equals 1 to n vi wi. And of course, the ui wi, that thing there, is u dot w, plus, and the other one is v dot w. So that is u plus v dotted with w equals u dot w plus v dot w. So this is sort of like, if you will, this is a distributive property. Next, if I have a constant, or a scalar, if you will, c is an r, then if I do cu, if I take that particular vector and dot it with a v, then what I get is, remember, cu, all the u coordinates have c times them in it. So this equals cui, those are what the components in each of the u coordinates is, times vi, I equals 1 to n. And the real numbers have an associativity, so I can move the c like the following, like so. And because c is multiplied to a sum, I can factor the c out. This is because of the distributivity of the real numbers. I can pull the c out, ui vi, and that's equal to c times u dot v. So I have cu. If I take that and then dot it with v, I can factor the c out front of the dot product. And so what do we have here? We have associativity, at least to the extent that you can with vectors. A couple of notes that you might want to know. When I do u dot u, you're going to get a sum, I equals 1 to n, and you have ui times ui. You match up the components. Well, that equals the sum, I equals 1 to n ui squared. So here, if you're adding, whenever you take a real number and square it, it's going to be non-negative. If you add up a bunch of non-negative numbers, then you automatically get something that is non-negative. So we have u dot u is greater than or equal to 0. Now, if you do have, if u dot u were equal to 0, remember this is a number now. When you take the dot product, you are adding up numbers. If it should happen that u dot u is the 0 number, then that means that this sum, I equals 1 to n of ui squared equals 0. I want you to think about this for a minute. if you had an equation like this, where both numbers squared, if you add them together, is equal to 0, then both pieces have to be 0. That means that x squared has to equal 0 and y squared would have to equal 0, but that means that x would have to equal 0 and y would have to equal 0, because you would have to have each and every piece equal to 0. So if this is equal to 0, that would tell me that each ui squared is equal to 0, which tells me that each ui equals 0. And then if every single entry in u is 0, then u is the 0 vector. If you examine these steps, you can see that I can reverse everything like so. I don't even need this if there. Basically what we have is that u dot u is equal to 0 if and only if u is the 0 vector. Now, you're used to this. The distance between x and 0 on a number line is given by this notation. The distance between the point AB, well, let's do it this way. The distance between the point XY and the origin in R squared is, this time we write, it depends. I've seen different notations, but a lot of them, they'll simply put the absolute value symbols around this, and you'll see that it's equal to x squared plus y squared, the square root of that. And similarly, the distance between x, y, z and 0, 0, 0 in R3 is given by absolute value x, y, z. That equals x squared plus y squared plus z squared, the square root of all this. You may not know this. I think I'm going to write it down. The square root, the definition of the square root, one of them is the square root of x squared. If you look at that version of the absolute value, then in 2 dimensions, this absolutely generalizes that. In 3 dimensions, this absolutely generalizes that as well. So what we do, the vector, let's call it u in Rn, has length given by this. We use sort of a double strike on the absolute value for a vector, and that equals the sum of the squares of its components. So u1 squared plus u2 squared plus ... plus un squared. That way, if you remember, one way to get a vector in Rn is to take the point that would be the end of the vector and subtract from it the origin, and then that's how you get a vector from that. Anyways, the distance, the very tip of that vector is from the origin, is identical to this computation. Anyways, we call this thing, we don't call it the length of u, although it is the length of u, the norm. of u. Let me go give a definition then. I think one way to think of the norm is the square root of u dot u. Or if you want, this version is just as useful. In fact, the second version is probably something more in line with statistical theory when they talk about things like the standard deviation versus the variance. The standard deviation might take this format, but the variance takes this format here. So make sure that you can see that this is the same as this. If u is u1 to un, then when you dot it with itself, you're going to take u1 times u1 plus u2 times u2 all the way up to un times un. Now, let C be in the real numbers and u be in Rn. Then Cu is a vector. Don't forget. Well, how long is that vector? Well, accordingly, this is going to be the square root of Cu dotted with the Cu. And so this is the same as, I'm going to try to make this, let's do it this way, so maybe you can see one of these. Cu will be Cu1 all the way up to Cun. And if I take that and dot it with the same thing, then I got to take the square root of all that. Well, accordingly, that's Cu1 times Cu1 plus Cu2 times Cu2, and you go all the way up to Cun times Cun. Of course, these dots are within the real numbers. Now, from all that, notice that because of the distributive property that I mentioned earlier, I can write this as c squared times u1 plus c squared times u2 all the way until I get to c squared un. Now I'm going to factor the c squared out of all this stuff. And what will be left? You'll have u1 squared plus u2 squared plus un squared. Now, all these numbers inside of the square root are non-negative, so I can break this up into the following. I can pull the cu squared out, and then I can leave the rest of the stuff behind. And as I mentioned above, the absolute value of c squared is the absolute value of the number c, and the rest of it is the norm of u. So I have something of, I don't know if you'd call it an associative property, but I guess all I'm saying is that you can sort of bring out the scalar, except you got to take the absolute value of it when you pull it out. Let me give you a definition. A vector u is a unit vector if the norm of u is equal to 1. We also call such vectors direction vectors. I seem to remember it's popular within calculus to refer to a unit vector as a direction vector. So with that in mind, let me do an example to maybe turn this make this more understandable. Let's find a unit vector in the direction of all right, right now we have a vector, but it's not going to be a unit vector. What I'm going to do is first let me find its length. So accordingly, I'm going to take -6 squared plus 4 squared plus -3 squared. Inside of there, I'm going to get 36 plus 16 is 52 plus 9 is 61. So the length of this vector is 61. So here's how you get yourself a unit vector. I guess you can call it a new vector. I don't know if you want to, but my unit vector that I can use is always this. Notice that 1 over the norm of u, this whole thing is just a number, so this is a multiple of u, which means that it's parallel to u. So it is in the same direction as u. So one vector that we may use, I don't want to call it v1, just v is good enough for me. There's the answer to our problem. Notice that if I want to do its norm, let's do the norm of v. That equals the norm of 1 over the norm of u times u. But remember, I said 1 over the norm of u is a number, a real number, so I can pull it out front in absolute values. Well, the norm of u, this thing right here, the norm of u is non-negative anyways. So with that being the case, I don't need the absolute values. So I have 1 over the norm of u times the norm of u. Well, this equals 1. So this is the standard process for producing a unit vector, is to divide by its length. And what you have left is a vector of unit length, which we call either a unit vector or direction vector. It all depends on what you want. So in our case, in my example that I was doing there, the v that I want equals 1 over the square root of 61 times the original vector, -6, 4, -3. This here is the vector that we're looking for this question here. The distance between vectors u and v is given by, we usually write this, dist u comma v, and that's the norm of u minus v. So as a quick example, I could let my u equal 0, -5, 2, and my v can equal -4, -1, 8. Then the distance between the two that's the norm of u minus v. And what you do in those cases is you just subtract the various pieces, like 0 minus -4 and square it, plus -5 minus -1 and you square it, plus 2 minus 8 squared, and we take the square root of the whole thing. I'll get 16 plus -5 plus 1 is -4, so that'll also be 16. plus 2 minus 8 is negative 6. If I square negative 6, I'll get 36. And that is the square root of 68. And for those that feel a need to simplify this is 2 radical 17. Now in r squared, we know that the lines y equal mx and y equal negative 1 over mx are perpendicular. So as a quick picture of this situation, you might have something like this. Let's say this is y equals mx. Then perpendicular to it, if I can hopefully get a picture that looks like this, y equals negative 1 over mx. Those two lines are perpendicular. Now I can get a vector on one of these, on this line here, on y equals mx. I can get a vector here by letting x go up to 1, and then y will equal m. So that vector that I just drew, let's call this u, will equal 1 for x, m for y. On the other hand, if I do the same thing, and let me extend it, this line this way, if I let this be the end of a vector going in this direction this time, make a big vector out of this. I'll call this v. That vector there, v, since the x part is 1, the y part, then when you plug x in for 1, you get negative 1 over m for y. So these two vectors are perpendicular. So I use this notation as perpendicular to 1, negative 1 m over m. Now notice that 1 over m is perpendicular to any vector parallel to 1, negative 1 over m. So L is 1 over m is perpendicular to any vector parallel to that one. Well, any vector parallel to 1, negative 1 over m is a multiple of that same vector. So what I mean is this. Let's put it this way. That is, I don't know what letter to use. We'll use A times 1, negative 1 over m is perpendicular to 1m for any A in R where A does not equal 0. So the reason I bring this up is this means that is, or that is, well, I guess that is 1m is perpendicular to m times 1, negative 1 over m. But when you multiply the m through, you get m negative 1. Notice that when I take the dot product of 1 over m with m negative 1, I get 1 times m minus m times 1, and that equals 0. What we try to do is, in fact, these two vectors have a dot product that is equal to 0. We extend this idea to Rn. Definition: vectors u and v in Rn. Now, unfortunately, they don't use the word perpendicular, but they do use this word, are orthogonal. And if you want to think of the word as perpendicular, that's fine. They are orthogonal if u dot v is equal to 0. In R2 and R3, orthogonal is the same as perpendicular. Now, perpendicularity is a little bit specific as to a geometric situation. Orthogonality includes more things than just perpendicular. For example, the 0 vector is orthogonal to every vector. So you couldn't include the 0 vector as orthogonal, as perpendicular, because the 0 vector, you wouldn't consider the 0 vector just being, I guess, a point. You wouldn't think of that as being perpendicular to any kind of a line, segment, or vector. Well, as an example, determine if u and v are orthogonal. And so the u that I'm going to give you is 12, 3, negative 5, and v will equal 2, negative 3, and 3. And so to see if they're orthogonal, let's take their dot product. So the first entry of u is 12 times the first entry of v plus the second entry of u times the second entry of v, and then plus the third entry of u times the third entry of v. And let's see what we have. 24 minus 9 minus 15 does indeed equal 0. So the answer, I guess, to this is yes. And we have something that is a Pythagorean theorem, and it goes like this. It says two vectors u and v in Rn are orthogonal if and only if u squared plus v squared equals u plus v squared. Now, I want you to see something for a minute before I do anything else. Let me go back to R2. Let's say you have a vector, and we'll call it u, and then another vector that we'll call v. If you'll remember, one of the ways I can get their sum is to create a new vector like this, sort of use a parallelogram to create my new vector here that goes from this spot to this spot here. See if I can make it so it doesn't mess up too much. So this is u plus v. Now let me draw a better picture over here somewhere. So we may have u, and then this may be v, not u again, but it's v this time. And the length connecting, the vector connecting the beginning to the end. Oh my Lord, for the life of me, I cannot get this thing straight. This vector that starts here and ends up here is u plus v. All this thing is saying is that the length of this plus the length of this, those things squared, is equal to the length of the vector squared if and only if they are orthogonal. What does that mean? Well, if u and v are orthogonal in R2, that means they meet at 90 degrees. So we would be expecting something like this. So we would expect the length of this squared plus the length, I better put v over here, the length of v squared to equal the hypotenuse squared, that is the Pythagorean theorem, only if they formed a right triangle or were orthogonal to each other. Let's start with u plus v squared. Remember that the rule, well, there's no square root when I do it this way. This is equal to u plus v dotted with u plus v. Now, according to some of the distribution rules, I can do this. U plus v dotted with u plus u plus v dotted with v. Then I could distribute again and get u dot u plus v dot u. And I can do the same for the other parentheses, u dot v plus v dot v. Now if you look, u dot u is the same as the norm of u squared. V dot u and u dot v are the same, so I have 2 times u dot v. And then I have v dot v, so that's the norm of v squared. So this is actually what u plus v squared equals. Now, u dot v equals 0 if and only if u and v are orthogonal. So the middle piece of this sum up here, this piece right here, is a 0 if and only if given u equals AB in R squared, determine the set of all vectors that are orthogonal to U. So what do all they look like? Well, let's take a look. We're looking for all those vectors whose dot product with AB is equal to 0. So let xy be such a vector. I have ax plus by equals 0, and that means that ax equals negative by. Now, I'm not going to divide by anything here just yet. In fact, I don't think I'm going to, because I don't know if a is 0 or b is 0. If both a and b are 0, then it really doesn't matter. Everything is orthogonal to the 0 vector. But in a situation like this, I can invent the solutions to this. If you look, it is true that a times b does equal negative b times a, isn't it? And so what I'm saying is I could let the x be the b's and let y be a, so that my xy can equal b negative a. Or it doesn't matter, or xy, if you wanted to switch it around a little bit, you could instead put the negative with the b and do this. Either one will work. But then take a look. If I take my AB and I take my, what do I want to use? B negative A, I get AB minus AB, and that's equal to 0. So the set of all vectors of this form here are the ones that will work. So I guess we could say that any vector and that would be the solution to that particular problem there. Next, consider a plane in R3 that goes through the origin. So what would look like, let me see if I can draw sort of a picture of how this would look. Here's supposed to be my plane, and then it's along, let's see here. There's the z-axis, and there's the y-axis, there's the x-axis. So let me pick something here that is a vector that emanates from there and goes straight up, like the z-axis does. Let's say this is my vector v, and it is perpendicular to that plane. Then let w be the plane. Then you can see that v is perpendicular to any vector that is in w. So v is perpendicular to any vector w in w. So what I can do is say v dot w equals 0 for every w in w. So what we do then is we say that v is in w, but we put this little perpendicular sign up there. So v is in the orthogonal complement of W. This brings up a definition. Let W be a subset of Rn. Define the orthogonal complement of W to be W with this little perpendicular set. We usually, from what I remember, we used to call such a set W perp. So isn't W perpendicular? And what this is going to equal is going to be the set of all vectors in Rn such that W dot V equals 0 for every W vector in W. Theorem. If W, the set W, subset of Rn, is a vector space, and since it's a subset of R to the n, that'd call it a vector subspace, but let's just say it's a vector space, then W perp is also a vector space. Well, for the proof, we already know that 0 is in W perp because 0 times anything in W is going to be, or 0 dotted with anything in W is going to be 0 because the 0 vector is orthogonal to everything, not just W. Next, if we have a real number, and I've got let's give me a V in W perp, then if W is in W, I can take my CV, dot it with W, and using the rules that we determined before, that I can pull out the C and still have V dot W. Well, since V is in W perp, this will be C times 0, and C is a real number, so that will just end up being 0. This implies that CV is in W perp. And well, I think you know where this is going. Now finally, if U and V are in W perp, and W is in W, then U plus V dotted with W equals, I can use the distributive property now, U dot W plus V dot W. But U is in W perp, so you get 0, and V is in W perp, so you get 0 for both of those. This is because U and V are in W perp, and that ends up being 0. So this implies that U plus V is in W perp. So this implies W perp is a subspace. Theorem. Let's go to matrices. Let A be in M by N. So it's an M by N matrix. What we have is that row A perp equals the null the null space of A. Let me fix my perp. And the column space of A perp equals the null space of A transpose. For the proof of this, I am going to pick an arbitrary vector inside of row A perp. So let's call it U. So I'm going to allow U to be in row A perp. Well, what does that mean? Then U dot R equals 0 for every R in row A. Then, when I take A times that particular vector, let me break A up into rows. R1, R2, up to Rm times U. And if I write it in a row format, you'll see, and these are all vectors, by the way, row vectors, if you will. That'll be row 1 dotted with U, row 2 dotted with U, all the way down to row M dotted with U. And I already know that U times each of those R's is equal to 0. So we get 0, 0, all the way down and, well, that's the 0 vector. So we have A times this U equals the 0 vector. This implies that U is in null of A. So what I did is I picked a vector, an arbitrary vector, inside of row A perp, and I showed that it was in the null space of A. So this implies, together this means that row A perp is a subset of null A. For the reversal, I'm going to choose next pick U to be in null A. So I'm picking U as an arbitrary vector in null A. I want to show that it's in row A perp. But here's what we know. We do know that AU is equal to the 0 vector. And so if I break that A up into rows like I did previously, row 1 up to row M, and I'll do exactly like I did before. I'll have R1 dot U all the way down to Rn dot U. That's an M down there. And I know that this is the 0 vector, so I know that each of these entries is 0. So U dotted with Ri equals 0 for every I from 1 to M. Now, row A is spanned by sum of the rows of A. So every vector R in row A can be written
as a sum of vectors, well, let's say better yet, a sum of row vectors in A. So like R can equal, I don't really care, A1 R1 plus A2 R2 plus dot 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 A M RM. So I don't necessarily need all the rows. Some of these AIs could be 0, no big deal. But then when I do U dot R, that equals U dot A1 R1 up to AM RM. And of course you can distribute the dot product through, and you can also use associativity combined, A1 U dot R1 plus dot 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 plus AM U dot RM. But I just went and showed this right here, we know to be true. So this will be A1 times 0 plus, and this will go on, plus AM dot 0, which is equal to the 0. And these are all zeros. It's equal to the 0 number, I suppose you would say. So what do we have? This implies that U is in row A perp. So what we have then is that the null space of A is a subset of row A perp. Since I showed subset both ways, this implies that both of them together implies that null A equals row A perp. The other part of the theorem, I'll leave it to you. You can pretty much follow exactly what I did to do it. Since W perp is a vector space, for W being a subset of R to the n. I'm not even sure W has to be a vector space for W perp to be a vector space. If W happens to be a vector space, then what would we know? If W was a vector space, I know that 0 would be in it, but I also know that the 0 vector is in W perp anyways. Next, what else would I have? I would have then that 0 is in W intersected with W perp because it's in both of those sets. And so 0 is a subset of W intersected with W perp. Now on the other hand, this time let W, the vector W, be in W intersect W perp. Then we would have W times or dotted with W equals 0. Why? Because that vector is in W, but that vector there is in W perp. So a vector in W times a vector in W perp is automatically 0. So what does this tell me? This tells me that W is equal to the 0 vector. And this implies then that W intersected with W perp is a subset of just the 0 vector. So what all did I just prove then? I went both directions. We have that the 0 vector is equal to W intersected with W perp.